Okay, good. So again, thanks everyone for joining. So I was saying, like the first lecture on the series was a bit more about introduction to the three-body problem and try to sort of introduce basic notions that appear and then have appeared throughout history and how people have been trying to use them and so on. In particular, one of the important notions that I touched upon was the notion of a global surface of section. So today what I'll try to do is try to take a more global topological approach by the notion of open books, and then try to move on into more like the contact and symplectic topological aspects of the problem. So this global topological approach. So let me start with a very general definition. So assume that M is some closed manifold. So a concrete open book decomposition on M is a fibration defined on M, but on the complement of some submanifold V, taking values in the circle, where here V is some closed codimension 2 submanifold with trivial number bundle. And such that I want this fibration pi, I'm going to call it pi, such that pi has a standard model near B of the following form. So I can find some coordinates on which my fibration is the angle coordinate on some color neighborhood of B. This color neighborhood sits inside M, and here are theta or polar coordinates on the 2 disk. So I'm assuming that B has trivial normal bundle, so I can always find trivializations of its normal bundle, which amount to taking some color neighborhood of it. So the picture is roughly like this. So we've got B here, and then I'm taking a color neighborhood of B. It's a 2 disk trivializing its normal bundle. And the fibers of this vibration, what we want to do is, in this color neighborhood, they're just radial. So they come in radially like this. So in other words, here B is usually called the binding of the open book. So in other words, this picture looks something like when I take a book and I open the book and I see all the pages of the book, and I basically glue the front lead to the back lead. This is what I'm seeing. So here, the fibers, the closure of the fibers of the vibration are usually called the pages. This is of the note like p theta, so this is the theta page, and the boundary of p theta is always p for every theta. So that's a local picture around the binding. So this is a concrete notion because, well, I have a given vibration, right? So in principle, I can sort of, you can imagine I can isotope the vibration around, and that's a different concrete open book. So there's also an abstract way to think about this. So an abstract open book is associated to data, which I'll denote by P phi, where here, where P is a typical fiber of the fibration, the page, the abstract data of a manifold, the page, and phi here is some monodromy. So in other words, a diffeomorphism of P. So an abstract open book associated to P and phi is the following manifold. Abstractly defined manifold is, well, denoted by M, open book associated to HP and monodromy phi is by definition, well, I take the corner neighborhood of phi, and then I just glue along the boundary of this a copy of the mapping torus associated to P phi. So here P is the mapping torus, which is just the quotient of the interval times P divided by the relation. I glue the top lid to the bottom lid with this diffeomorphism. So this is a mapping torus. Okay. So here in this picture, P is the data of the page. Of course, it extends away from the binding, and well, the claim here is that it's a fact that, well, if you give me a concrete open book, I can realize it as an abstract open book for a suitable monodromy phi, and the page is just the fiber of the fibration, and vice versa. I mean, the abstract notion clearly inherits the fibration over the circle, precisely because this guy fibers over the circle, and I can just take the angle coordinate here, and the gluing is in such a way that that this glues well. Well, I forgot to assume. Well, sorry, the monodromy needs to satisfy that the restricted to the boundary is the identity. Okay. So if I assume that the monodromy restricted to the boundary is the identity, then this gluing is well defined. So the fact is that the abstract notion, let's say, is up to isotopy equivalent to the concrete notion. With this up to isotopy, for the purposes of topology, is fine, right? I mean, I can work up to isotopy in topology, but if I want to do some dynamics, then dynamical systems tend to be very sensitive to isotopies. So usually working with the abstract notion is not the best. So you usually want to be working with the concrete notion for dynamics. So this is best for dynamics. I mean, what we will want to do is, you give me a dynamical system, I want to find some sort of embedded open book which is adapted in a suitable sense to the dynamical system. But if I sort of isotope my open book, I mean, it might not be adapted anymore. So that's basically the idea of what we're trying to do. Okay. So give me a bunch of examples. So the first example, this is the most trivial example you can think of, is just a three-sphere, which abstractly is given by the open book associated to a two-disk, and monodromy is the identity map. And a concrete way of viewing this is, I think of S3 as the pairs Z1, Z2 in C2 with norms 1. And I just define the fibration by projecting to the first coordinate divided by its norm. So this is well defined away from B, which is Z 1 equals 0 inside S3. Okay. So it's not hard to see that when you define this vibration like this, well, the monodromy is trivial. In fact, the fibers are the two-this, and if I'm giving a monodromy a diffeomorphism of the two-this, haptoisotopy has to be the identity. So in other words, the only open book that you could have whose page is a two-disk is precisely S3. So let me maybe draw a picture. So the picture of the trivial open book on S3 is, well, the following. So I want to think of S3 as obtained by gluing two solid tori along the boundary. So here what I'm drawing is, you need to think this is a solid torus, which I move around sort of the S1, in S1 direction, which I'm not seeing. So here's a circle. And the fibers of this open book look something like this. The pages are disks, and they have a following topology. So this is a projected version. So if you want a bit of a more true picture, is this circle is the unknot in S3. So it bounds a disk. And the pages of the open book look something like this. So here's the plane in S3. In S3, I'm just thinking in terms of adding a point at infinity to R3. So here, the plane compactified is precisely S2, sitting inside S3 as the equator. Okay, so this is a trivial open book on S3. Another way to think about the trivial open book is, well, it can be obtained by gluing two solid tori along the boundary. Formation of the solid tori in a suitable way, as follows. So another way to obtain this open book is by taking a copy of the solid torus, foliated precisely in this picture, where the pages look like this. And I take another solid torus. Here you need to think that I'm gluing top to the bottom, right? So it's a glue by the identity. And similarly here, there's a gluing procedure. I just glue by the identity, and here I take the foliation by disks. And well, I just glue the boundary of this to this, mapping the circle boundary of one of these disks to the circle of one of the other fibers. Okay. So yeah, so I'm using the Higgs splitting on S3. So S3 is T2 union T2 along the boundary. So I'm using the genus 1 Higgs splitting of S3 to obtain this open book. Any more questions? Okay. There's also another open book on S3, which is not the trivial one, which is obtained by a well-defined notion of stabilization of an open book, which is the following. So let's say example 1 prime is S3 is also the open book associated to the page V star S1, so the annulus, and the monodromy, the daintus toll. So here toll is the daintus along the zero section. So the standard daintus, right? So, and one way to visualize it is also by a picture like this, which is a bit harder to draw. I mean, I'm going to try, but so you take the same solid torus on the one side, so whose foliation by pages is well, the radial ones. And now, rather than taking the second solid torus, I will take solid torus whose foliation looks a bit different. So it looks something like this. You need to think, what's the best way of putting here an annulus whose boundary is precisely this circle union this other circle here. So well, it has to look something like this. This is what the pages look like on the other side. You can have some imagination here, but what you're doing is you're gluing an annulus to another annulus along the boundary. Well, and that's giving you the page. It's also obtained by gluing to manually by the boundary. And well, you need to do a bit of work to see that the monodromy is precisely the daintus, but a concrete way of realizing this is by looking at the Hopf link, which is just Z1 times Z2 equals 0 inside S3. This is the Hopf link. And so this is, in the picture above, is just the union of this circle with the circle that goes through infinity. So that's the Hopf link. And the fibration is defined in the complement of the Hopf link to S1. Mapping the pair to 1 Z2 to their product divided by their norm. And so this is a concrete realization of this abstract open book.
Sorry, could you repeat on the last drawing how you are gluing the pages on each of the toruses? It's all right.
Yeah, no problem. So here, you've got this annulus with 2 boundary components. So this circle and the other circle, which is the core of the first solid torus. And here, what I'm trying to draw is another annulus whose boundary is the union of this circle, the core, with one of these sort of meridian circles. So you need to think this annulus is a bit twisted. So it looks something like this, and then it comes back from here, and then it sort of wraps around in some funny way. I mean, the best approach probably is to draw it yourself and see what you can actually do. So there's a picture in the notes, which is probably better than my pictures on the board for you to see. But yeah, that's roughly the idea. Any more questions?
Yes, when you have a concrete open book decomposition, what is the monodromy?
So, right. So, by definition, concrete open books has a fibration and a complement of something. And if you want to actually construct the monodromy, okay, there are several ways that you can actually do that. But if you want, the one that I know is well, you can sort of. I mean, the monodromy is a topological object, right? But one way to obtain it is actually a return map of associated to a connection on this fibration, if you want. So you can take a connection whose which is tangent to the pages. So if you want a symplectic connection, if you know what that is, and then you just take the return map of that, and that's going to be your monodromy. I mean, there's something to do near the boundary. You want the monodromy to be the identity at the boundary. So yeah, you need to be a bit careful. So the construction is not obvious at all. Let me do one further example, which appears in the three-body problem as well as S3, which is RP3. Nice. Because as we've seen, this is well, the regularized energy level sets in the planar problem. So this is the open book with page, the annulus, and now rather than have it in tow, because well, this is the quotient of S3 by a double cover, well, I will see is the square of a dangerous. So this is, well, the length space L21, and you can actually prove more generally that LP P-1 is an open book associated with page T stars 1, thought to the P for P greater or equal than 1, and LP1 is same thing, but where P now is less or equal than 0. So this actually gives you all the possible open books where the page is in annulus, right? So because the mapping class group of this guy is generated by tau. So every monodromy looks like a power of tau, and this is everything that you can get. I mean, for us, the important open book will be this one. Okay, so why am I talking about open books? Well, they're fairly general objects. They actually appear everywhere. So we have the following theorem, which says that, well, if M is closed and its dimension is odd, three manifolds, for example, then M admits an open book. Okay, so in other words, I mean, this open book construction is not sort of some esoteric thing. Actually, you can realize every odd-dimensional closed manifold via this construction, which is something quite powerful. I mean, in dimension 3, I mean, this already has some history. Dimension 3 was proven originally by Alexander, and then Wilken-Kemper in the simply connected case, dimension at least 7, and then Lawson dropped the simply connected assumption also in dimension at least 7. And then Quinn, dimension at least 5. So, you know, it's a number of names associated to this. So in particular, every 3 manifold, you can sort of realize it as an open book, which is something that is actually not too terribly difficult to prove if you assume some other structural results, some sort of structural results for a manifold. Okay, so that's some topological digression. So now we go back to dynamics. So far the discussion has been sort of smooth or topological, but now if you give me a dynamical system, so if you give me an autonomous flow, on M, so well, let's say that the dimension of M is odd. So that the above theorem applies. So, well, doesn't really matter. But like, we say that a concrete open book, which I'll denote by sometimes I'll denote by the pair pi B for the binding, so projection and binding. So a concrete open book is adapted to the dynamics. If the following conditions hold. So, well, first of all, I mean, basically, what we want is that the dynamical system is in some sense compatible with the underlying geometric structure. And concretely, what that means is the following two conditions. So I want first that B is invariant under the flow. And the second condition that I want is that for every x that is not in B, and for every page, there exist positive times and negative times, depending on x, such that phi of plus minus x of x lies in the interior of P. Okay, so, in other words, any point which is not in the binding, its orbit intersects the interior of a page in the future and in the past. So this should be similar to you by now, because this is very similar to the definition of a lower surface of section, and it's basically a high dimensional version of it. Right? Lower surface of section, I just asked that the boundary is a bunch of orbits, and dimension 1, well, that's basically the same thing as being invariant under the flow. So in other words, every page of the open book, whenever the dynamics is adapted to the open book, is what I will call a global hypersurface of section, as a high dimensional definition or generalization of what a global surface of section is. So in other words, each page is a global hypersurface of section. Or sometimes, I don't know, global hypersurface of section. Okay. I mean, the important thing is that the page is codimension 1 in the manifold. So, I mean, if you want, the definition is that P inside M is codimension 1. That if its boundary, its boundary, if non-empty, well, in the case of an open book, it is non-empty, it's the binding. It's flow invariant. And well, second condition is satisfied. On two poles for P. So whenever I have a dynamical system, and say in a high dimensional manifolds, and I have an open book with adapted to dynamics, well, I have a Poincare return. So we have the associated return map. This is just a map defined on the interior of the page by just look at the first return time of the flow. So here tau of x is a minimum positive time such that Pt of x lies in the interior of X, in the interior of P.
Agustin, sorry. Agustin,
Yeah.
you don't ask transversality of the flow with respect to the
Okay. It should be, yeah, I guess you're right.
continuity of the Poincaré map.
Yeah, so it should be part of the definition actually. So yeah, you're right. So 1, 3, sort of phi t is transverse to the interior of P for every page P. Yeah, so thanks. Okay.
What did you write here? The minimum of what?
Minimum of t. This is supposed to be a t. So positive t such that phi t of x is again in the interior. So this is the Poincaré map that we've seen before, only just in a high dimensional setup. Okay, so let me do what for me will be a fundamental example. Let me first actually mention one, well, sort of basic example, A. So if you look at the Hopf flow in S3, so here you look at the Hopf vibration, which is just by definition, just the quotient in projective space when I see S2 as P1, so P1. So this is a Hopf map. So the fibers of this guy can be parameterized by e to the it. So 1 to 2. So these are the fibers of the Hopf map. So well, it's not hard to show that this flow, sort of when you flow in the fibers, is adapted to the trivial open book as well as the stabilized version. So this is what's called the Hopf flow. So the Hopf flow is adapted to the trivial open book and its stabilized version. And stabilization. If you want, you can prove this just by looking at the Hager diagrams of the whole. If you understand well enough the geometric picture, sort of this is more or less clear. But this example, although very sort of elementary, actually does show up in the three-body problem because, well, remember that the geodesic flow in S2 appeared in the three-body problem, and the double cover of S2 is S3. Of RP3 is S3. So you can take the double cover of the open book in RP3 and sort of lift it, and what you will find is basically that the stabilized open book upstairs projects down to the open book in RP3, and the open book in RP3, as we will see now, is adapted to the geodesic flow. So you can lift it up and you see the Hopf vibration upstairs being adapted to the stabilized open book. So this is a picture that you guys should have in mind. So the fundamental example for me is the geodesic flow on a sphere. So this is on Sn. So this is a geodesic flow on a round sphere. Fundamental from the top one. So I will think of T star N as the pairs psi eta in T star Rn plus 1, whose the norm of psi here is 1, and the inner product of sine eta is 0. So I take the round metric, and basically I have an associated unit potential bundle of Sn, which is just those covectors of norm 1. So those eta whose norm is 1. And while I look at the geodesic flow, which is a round geodesic flow, well, you can sort of check that it's generated by a vector field, which looks like this. So X. So this, when I use the inner product, I mean, this is, you need to sum over the indices. So this is a geodesic vector field. So this generates the geodesic flow. And the binding, well, it's just I drop one of the coordinates. So it's just those pairs, psi eta, whose last coordinate, let's say psi n, and eta n is 0. So here I'm indexing everything from 0 to n. So this is the unit potential bundle of Sn minus 1. So this is, Sn minus 1, the equator is totally geodesic inside Sn, so this is flow invariant, right? This is invariant under the geodesic flow. Okay, and then I just look at the following concrete open book decomposition, which I'll call pi g for the geodesic open book, which is defined on the complement of the binding B, taking values in this one, which is what you might think it is. So it's just I map psi eta to the quotient of, I take the last two coordinates, I put them in some complex number, and then I just divide by its norm, and this is an element in the circle. Right? So this is obviously defined away from the binding B, and those two things are 0. And so here, what you can check is that if you look at the theta page, so the fiber over theta, this is just a copy of the unit disk cotangent bundle of Sn minus 1. So the picture is, well, the following. You should think of the Birkhoff annulus that we discussed last time, and this is just a generalized version of that. So this is, you look at the sphere. So this is Sn, and here's Sn minus 1. And I look at the equator, right, Sn minus 1, but I look at every covector or vector that points upwards. And then I move them around Sn minus 1 as well. So here I've got an n minus 1 dimensional disk, right? So this is an n minus 1 dimensional disk worth of directions which are positive, and this is the page, the 0 page of the open book. So this is what this is like a copy of p star Sn minus 1. Right? I have the base is the equator, the fiber is this disk. Then I move the point around the equator, and well, this is higher dimensional version of the Birkhoff annulus that we saw last time. Just put n everywhere. So this is, I don't know how to call this, so I'll call it a Birkhoff annulus. And if you guys have a better name for it, I don't know, Birkhoff unit disk cotangent bundle of Sn minus 1 is not very good. But so I'll call it a Birkhoff annulus. So what you have to do, this is the 0 page, right? So this is P0. So how do you obtain all the other pages? You just take the page and just flow it with the geodesic flow, and you'll hit hit the other page. Because this guy is flow invariant, flowing with the geodesic flow does not change the boundary. So every page actually has the same boundary, the equator. So let's try to draw how this looks like. So this page, the Berkeley finalist is precisely psi n equals 0, eta n positive. So eta n is this direction. So now hit it with a geodesic flow. And what do you get? Well, if you start looking at this picture, so this guys will want to open up like this. This is invariant, and this vector, which is the one that points maximally up, is the one that reaches the furthest point up here. So what you will see is something that looks like this. So here's a maximal sort of vector that you achieved by this guy here in time. Let's say you flow times theta. And these guys will open up to something that looks like this. So the only way to reach this point is through a vector that points like this. The only way to reach this point from the other direction is by another one on the other side and similar here. So this opens up into a weird, funny way. But this is basically how it looks like. So when you've done sort of, every geodesic is 2 pi periodic. So when you've done times pi over 2, you're up here, and you have all possible directions so you can actually choose. But before that, you don't never actually reach here. So this is roughly how the pages of the geodesic open book look like smoothly. And you can actually check that this open book is adapted to the geodesic flow is via reasonably easy computation. So you can look at the angle coordinate omega g, which is just the derivative of pg, which is, as a one term, is just eta n d psi n minus psi n d n divided by psi n squared plus eta n squared. So this is the angle coordinate, the angle sort of one form associated to this open book projection, this one here. And well, you can check that if you plug in the geodesic vector field x, you will get exactly 1. So this one form is dual to the geodesic vector field. And this precisely means that the open book is adapted to the geodesic flow. I mean, this, as long as you're away from B, and this is well defined away from B. So this scaling is what gives you this number 1. This is adapted to the geodesic flow. I mean, it's adapted to the geodesic flow by construction. Because I just told you, well, look at the first page and it's flow with the geodesic flow, and then it's obviously adapted. But this is sort of a more formal way to prove it. This just means that the vector field generating the flow is transversed to the page in the interior. And here you recover the open book that I said before for n equals 2. The unit contention bundle of S2 is RP3, and this is a sort of high dimensional version of the open book in RP3. So n equals 2, the unit contention bundle of S2 is RP3. And well, I told you that the open book that you have there, well, the page is the Verkov annulus if you want, and then monodromy is the square root twist. And the square, I mean, it's related that you have sort of 2 weird looking pages. It's on the North Pole and the South Pole, the pages look funny. I'll try to make that more precise, but this is why I have a square. And for S star S N, you can actually, well, what's the monodromy of the open book? It's a generalization of the Dane twist, which is usually called the Densidal twist. So this is.
Can I go to my usual rant?
What?
My usual rant.
Yeah, but no, because now I have it in N. Okay, so Arnold defined the Dane twist for the case of D star is 2 before Seidel did. And Seidel generalized Arnold's constructor to any dimension. Does that please you, Paul? Yeah, you're right. So this Arnold was also part of the story here. So here we've got tau squared, where tau is the Arnold then Seidel twist. Well, I'm not exactly going to tell you what this map is, but you sort of, it's defined using the fact that the geodesic flow on the sphere is totally periodic. So you need to sort of interpolate between doing a full turn and doing sort of a pi times pi turn. So on the 0 section is precisely the antipodal map, as is the case of the standard Dane twist. And away from the 0 section, sufficiently away is the identity. So this is, I mean, this is a rough sketch of what this map is. Anyways, so this is my sort of topological introduction to sort of open books, and these are the objects that would appear, surprisingly or not, in the three-body problem. What should I erase? Any questions before I move into more geometric things? So this is where the geometry starts then. So I will try to cover the very basics of symplectic and contact geometry. So this will be a very sort of quick and rough introduction to the subject for those who have never seen it before. But you know, what you need to think is that these are the geometries underlying classical mechanics. So symplectic geometry is just, you know, the formalization of what you see in phase space. And contact geometry is an odd dimensional version whenever you fix the energy level sets and the Hamiltonian is sufficiently convex such that you have some sort of contact condition. So this is roughly this guy. So symplectic geometry roughly speaking is a geometry of phase space. Remember, phase space is a configuration space of position and velocities of a classical particle. So formally, symplectic manifold is just a pair of a manifold M, which is 2n dimensional, so even dimensional manifold with 2 form omega. Define on M satisfying 2 conditions. So this is a closed 2 form. So its exterior derivative is 0, and it is non-degenerate in the sense that when I look at its top exterior power, so when I look at the wedge of n copies with itself, which is the top power that I can possibly do, this is nowhere vanishing. This is nowhere 0, so in other words, this is a volume form. And it's not hard to check that non-degeneracy in this sense is equivalent to the following. This is equivalent to the map going from vector fields on M to one forms on N, defined by contracting with omega. So my notation for contraction is I x omega. So omega, if I make it eat x, this is now a 1 form. So this should be an isomorphism. So this is equivalent to the non-degeneracy condition. This is non-degeneracy. Okay, so all very nice and good. If you've never seen this before, then maybe it doesn't make much sense at this point. So it's not very enlightening. But what's the point of this? Is well to actually generalize the situation when you have phase space. So what's the fundamental example from classical mechanics? Well, you take phase space, which is just R2n, and the standard omega. So omega, I didn't say it, but omega is called the symplectic form. So the standard symplectic form on R2n is defined by, well, you take QP, which are the coordinates on R2n. This is position, and this is momenta. And the standard symplectic form is just defined by, and here, I'll make a sign convention, which is not what everyone does. So I'll just take it minus the derivative of lambda standard. So this is dq, which dp, and here lambda standard is defined by p dq. And this is sort of shorthand notation for the sum from I equals 1 to n of dqi, which dpi, and this is shorthand notation for sum from 1 to n of pi dqi. And let me just mention again that this is, the minus here is a subject of debate for symplectic geometry. Sort of all the possible sign conventions have a use in the literature, and it's very annoying. But what you would like to have right in the end is the Hamilton equations, which I'll write down now. Before I do that, let me mention another fundamental example, which is a cotangent bundle. So you take a manifold Q, and you take the omega standard. This is also called the standard symplectic form, which is by definition the derivative of minus the derivative of lambda standard, and lambda standard is defined as well. So you stand on a point in T star Q. Sorry, so here I will want to define it on T star Q. And so you stand on a point QP, which is a position covector over that position. This is applied to eta, which is a point in the tangent space of T star Q, and this is just P applied to the derivative of QP of pi of eta, where here pi is the standard projection to Q. So here QP is in Q, and this lies in T, Q, Q star. So P eats vectors which are tangent to Q at small q, and I'm just taking eta, which is tangent to the cotangent bundle of Q. I take its differential under pi, and I make it eat E. This is a very sort of tautological and complicated way of just writing down these equations, if you want, in local coordinates. So if you didn't understand this sort of this formula, just think of that, because, well, every symplectic manifold actually looks locally like faces, and that's the whole point. So we have the following theorem to Darboux. Which says that for every point in a symplectic manifold and omega, then there exist local charts. So local chart U containing P, such that, well, if I restrict omega to U, this is isomorphic to phase space. So, in other words, every symplectic manifold locally looks like the most standard thing that you can have. And here isomorphic means a very precise thing. So here, an isomorphism of symplectic manifolds is just what you think it is. So it's a diffeomorphism which pulls back the one symplectic form to the other. So two things are isomorphic. There exists some diffeomorphism from M1 to M2, such that if I pull back omega 1, I get omega 2, I get omega 1. So this is what's called a symplectomorphism. So in particular, if you have symplectomorphism, well, it preserves the symplectic volume. So just by taking the wedge n times of this thing, so omega 2 to the n is omega 1 to the n. So preserves volume. So I mean, preserving the symplectic form is stronger than preserving the volume. The symplectic form really should be thought of as a two-dimensional object, that it measures two-dimensional areas. It's a sum of sort of wedges of two one forms. So those sums of wedges are just two-dimensional area forms. And so Darboux's theorem usually sort of is sort of interpreted as saying that symplectic manifolds locally do not have local invariance because they all look locally the same. So it's not like in Riemann geometry, in which a Riemann manifold, you have curvature and sort of that's a local invariance. So this is not the case. So symplectic manifolds are more sort of global objects. But basically, the spaces in which I can do Hamiltonian dynamics, so which I can write down the Hamilton's equations and solve them and sort of study how particles are moving. So you should think of cotangent bundles. It's just geometric space, but it's modeling. If you want to write down some mechanical system, what you should think is there's a particle that's moving in Q, and I'm remembering its position in Q, and I'm also remembering its velocity in the fiber. That's what's happening. So as I said, sort of symplectic manifolds are the spaces when we can do Hamiltonian dynamics. So what is Hamiltonian dynamics? So you give me a Hamiltonian, which is the energy function of the system. So H, which usually depends on time. So just a time parameter. And so it takes points in your manifold M and it spits out the real values. Let's say it's a smooth map. This is called the Hamiltonian. So here usually we denote h sub t by ht dot. And so if you start with a Hamiltonian function, so an energy function for some mechanical system, the Hamiltonian formalism, what it's supposed to do for you, is supposed to spit out a vector field, so a dynamical system. So what the symplectic form does for you, so that the symplectic formalism is you give me H and I give you back a Hamiltonian vector field. Denoted x h of t and defined implicitly by the equation the contraction of this vector field of omega has to be, by definition, the differential of ht. So this as one. And remember that from the definition of a symplectic form, sort of the contracting map is supposed to be an isomorphism, so there has to be a unique vector field corresponding to the differential of my Hamiltonian. So this is a well-defined notion, just by non-degeneracy of omega. So this is well-defined. But sort of here, again, depending on the sign convention that you do before, there's a minus or there's not. So in this convention, there's not. Because, well, the fundamental example that you should have in mind is, well, what happens when I take phase space? So R2n with its standard symplectic form. So, well, you can actually check that the Hamiltonian vector field xh, just drop the t for convenience, is just the derivative of h with respect to p partial q minus the derivative of h partial q partial p. So in other words, a solution to the Hamiltonian flow is just a solution to the Hamiltonian equation. xt, qt, pt solves x dot xh applied to x if and only if it solves the Hamilton's equations, which are q dot equals partial h partial p and p dot minus partial h partial q. So what does it mean? Sort of, by the Giroux theorem, locally, every symplectic manifold is phase space. So solution to the Hamiltonian flow on on a global symplectic manifold locally is always solution to the Hamiltonian equations. So this is just by definition. So we should think symplectic manifold is just some global sort of version of what you do on phase space. So very good. So how does the principle of conservation of energy, which we used last time on the three-body problem, look like in this formalism? So you can write it down very easily. So theorem, this is called conservation of energy. So if you take a function which is autonomous, so it does not depend on time. So this means time independent. Then the derivative of h applied to its own Hamiltonian vector field has to vanish identically. In other words, i.e., xh is tangent to every level set. It's tangent to every level set of h. Or in other words, every level set of h is invariant under the Hamiltonian flow. Okay, so we've used this in the first lecture for the case of the three-body problem, because we actually had an autonomous Hamiltonian by some magic trick. And actually the proof of this sort of conservation of energy is just like, it fits into one line. It's very simple. So, you know, the proof is you do the h of xh. By definition, this is just a contraction omega by xh applied to xh. But this is omega of xh, but omega is Q-symmetric, so this has to be 0. This is a two-fold. So that's a one-line proof of a very fundamental principle in physics. This is why sort of it's kind of a useful formula. Okay. So this is sort of the crash introduction to symplectic geometry. So let me do the crash introduction to contact geometry. And then we'll take a break. So what's contact geometry? So, well, similarly is the geometry of, well, convex in some sort of ill-defined way at this point of convex level sets. So by convex, well, I will explain what I mean later, but you should think, well, I take a level set and if my Hamiltonian is good enough, then I have a contact condition. So formally, what does that mean? So it means the following. So definition. So strict contact manifold is a pair x alpha, where x is 2n-1 dimensional, so it's odd dimensional. And here, alpha is a one form on x, which is called a contact form. And the contact form is supposed to satisfy the contact condition, which is defined as follows. So such that the following condition holds when I look at alpha and I wedge it with the alpha to the n-1, which is the top form. This is lower vanishing. i.e. a volume form. And well, if you look at this expression, this is a bit funny looking, but it means if I look at the kernel of alpha, which is a codimension 1 distribution on the tangent bundle, so I'm choosing a hyperplane on each tangent space, what this means is that the alpha is a symplectic form on that kernel. It's just by just killing this guy. So this is equivalent to the alpha restricted to psi is symplectic, where psi here is the kernel of alpha, which is usually called the contact distribution. So this is a distribution inside the tangent bundle of X. Again, I'm choosing on each point of X, I'm choosing a co-dimension 1 subspace. And globally, my one form defining this distribution is supposed to satisfy a differential equation. So this is, there's a derivative here. So there's some derivatives involved, some geometric equation rather than topological in principle. So, okay, that's all nice and good, right? But what does it mean? So maybe I'll just give you a bunch of examples. So example is, well, the standard example, as we had a standard symplectic manifold, we have a standard contact manifold. So the standard contact distribution is the kernel of standard contact form, and here the standard contact form is by definition dz minus pbq, where I'm taking coordinates z, qp in R2 and R plus R2n minus R n minus 1 plus Rn minus 1. I mean, it's just some one form defined like this. So, and another example that is interesting is, well, the first jet bundle. So you take a manifold Q and I look at the first jet bundle of Q, which is by definition denoted by J1Q. This is the first jet bundle. This is, well, roughly speaking, this is the space of all possible first derivatives of maps of functions defined on Q. So this is space of all possible first derivatives of maps from Q to R. Well, the fiber over a point is, well, tuples of derivatives of a function. So let me just write it down. So the fiber of J1 over a point Q is just the space of all pairs Q, f of Q, first derivative at Q of f of a function from, for all possible functions defined on some open set containing Q. So, I look at the germ of all smooth functions around a point, and this is the tuple of first derivatives. So value, and then first derivative here. So in other words, globally, J1 of Q is diffeomorphic to R times T star Q. But here, if we take coordinate Z, which is what's keeping track of the function value, then the contact form is just alpha is dz minus or plus lambda standard. The lambda standard is well, the primitive of the standard symplectic form monomial. It's called the standard Liouville form. So this is the contact form. So in other words, J1Q alpha is a contact form or strict contact manifold. The word strict just means that I'm actually specifying a contact form as opposed to specifying the contact distribution. So let me just pause and say a few words about sort of where the contact condition arises historically, if you want. So it originally comes from work of Sophus-Lie, where he was working on differential equations. You need to think, first jet space is the natural space that you will want to look at if you're looking at the differential equation of order 1, right? So you're looking at maps up to first derivative. So what Sophus-Lie was considering sort of transformations which preserve a certain geometry, and that geometry is precisely the geometry given by the contact form. Sort of, he didn't phrase it in this terms, of course, but that's where you can trace originally the appearance of the contact condition originally. And then people took it up and did different things. But anyways, so let me give you some sort of intuitive way of understanding what the contact condition means as well. Via the following notion. So recall from differential geometry the theorem of Frobenius. Which can be stated as follows. So if the derivative of alpha restricted to the kernel of alpha is vanishing, then the kernel of alpha is the foliation. In other words, I can integrate it. This on the nose is a codimension 1 distribution of the tangent bundle. I can integrate it to a foliation on the manifold if this condition holds. So this is a very classical theorem. So the contact condition is the extreme opposite of this condition because I'm asking, that the derivative of alpha restricted to the kernel of alpha is symplectic. So it's non-degenerate. It's the most different thing that you can possibly be from 0. So it sees every possible direction. So the contact condition is very much not a foliation. So it's a maximally non-integrable distribution. So, contact condition is the opposite. I.e., it's maximally non-integrability condition. So, the hyperplane distribution needs to twist enough such that you can actually not find integrals of manifolds to this distribution, intuitively speaking. And well, you can actually make that slightly quantitative. You can actually show that the dimension of the submanifolds, which are actually tangent to the distribution, are at most n-1, if the dimension of your manifold is 2n-1. And those are called the submanifolds which are tangent to the kernel to the contact distribution are called the isotropics, and the maximally the ones which have maximal dimension are called the Johnians. And those are actually very important objects in many different branches of maths and physics as well. So we also have a Darboux theorem for contact manifolds. Well, every contact manifold locally looks like standard contact manifold. So again, contact manifolds do not have local invariance, so they are global objects. And in principle, they are geometric objects. Okay. So as I said before, in principle, we're looking at the geometry of phase space when we're doing symplectic geometry, and we have Hamiltonian dynamics. Here now, in the odd dimensional world, we're looking at a geometry of level sets, but we also have a dynamical system associated to such a problem, and this is the wave dynamics, which is the analogous version of Hamiltonian dynamics in this setup. So how does this work? So you give me a contact form alpha, and I spit out for you a vector field R alpha, which is called the rate vector field. And similarly, as with the Hamiltonian vector field, it is defined in an implicit way. So it's defined by two conditions that the derivative of alpha, when I make it eat R alpha, this is 0. And alpha applied to R alpha needs to be constant equal to 1. So why does this give me a well-defined vector field R alpha? Well, because of the following. So, the contact condition, as I said before, means that the derivative of alpha restricted to psi is positive, is in symplectic form. So this condition, means that the wave vector field precisely points in a transverse direction to the contact distribution. So this means that here psi, which is the kernel of alpha, and the kernel of the alpha is transverse because, the alpha here is positive. So our alpha needs to point in a transverse direction. And the second condition is a normalization condition. So I just pick precisely the direction on which given by the co-orientation given by alpha. So this is alpha positive, here is alpha negative. I'm sort of normalizing my vector field to point transversely. Okay, so in other words, we've got a geometric distribution psi, and we've got, whenever you give me a contact form for psi, I have an associated dynamical system. So you've got geometry and dynamics sort of playing with each other. Okay. Any questions? Okay, so I can look at the rate flow phi t, which is the flow of R alpha. And what does it do to the contact form? Well, the main point is that it preserves it. So, you can use the Cartan formula to show this. So this is the Lie derivative of alpha in the rate direction. So I use the Cartan formula here. And by definition, this term is 0, and this term is constant equal to 1, so its derivative is 0. So this is 0. So the derivative of this one form is 0, so it has to be constant. So in other words, phi t alpha is what it does at time 0. So this is alpha because this is the identity. So in other words, the rate flow preserves alpha, so it preserves all the geometry. So it preserves the kernel and it preserves the one form. And similarly, you can do the same computation for a symplectic form for the Hamiltonian flow, and you see that it preserves the symplectic form. Let's do that computation. So similarly, if we look at the Hamiltonian flow of a Hamiltonian, when we look at the derivative of the fullback under this flow of the symplectic form omega, this is by the Cartan formula. This is the, well, first of all, this is the derivative with respect to the Hamiltonian vector field of omega, and then by the Cartan formula, this is it's the omega plus d of omega, so this is 0. By definition of omega, it's closed, and this is the differential of h by the definition of the Hamiltonian flow. So this is the derivative squared of a function, but exterior derivative squares to 0, so this is 0. So we get that. Okay, so in contact geometry, we've got a very special dynamical system, which is wave dynamics. It preserves all the geometry. In symplectic geometry, we also have a very special flow, which is the Hamiltonian flow, and also preserves the geometry, preserves omega. In particular, a Hamiltonian flow preserves the volume of a manifold. And before I take the break, let me just tie the two notions together. So that's symplectic and contact worlds via the following. So what's the bridge between the worlds? So the bridge between the contact and symplectic worlds is the following. So assume that omega is an exact symplectic form. So it's the derivative of lambda, some lambda. And in the situation, we have the associated Liouville vector field. V defined via the equation. So the contraction of the symplectic form via V needs to be lambda. And again, this is given me a well-defined vector field by non-degeneracy of omega. But what is this vector field doing? We saw that the vector field and the Hamiltonian vector field preserve the corresponding forms, in particular preserve the corresponding geometries. The Liouville vector field is doing something similar, but not exactly. So it's actually exponentiating the volume rather than preserving it. So what's happening is that when I look at the Lie derivative of omega with respect to V, so the derivative of omega with respect to V, this is again the third formula. So this is 0. This is by definition lambda, so this is d lambda, which is omega. So if the derivative of omega is omega, then when I look at the flow of V, and I pull back omega, I just need to have the exponential times omega. And this is what solves the equation. So in other words, the Liouville flow is a symplectic dilation. It doesn't really preserve omega, but it preserves up to an exponential factor. So when you flow, the volume is getting bigger and bigger exponentially. Okay, so what can I do with my Liouville vector field? Well, I can use it to cook up a contact form if the following situation holds. So assume that some submanifold X inside M omega, where omega is exact, is a co-oriented codimension 1 submanifold, and assume that the Liouville vector field associated to lambda is positively transverse to X. So, you have X here sitting inside M, and the Liouville vector field is transverse according to the co-orientation of X. So this is M. So what happens in this situation? Well, I can actually obtain a contact form on X. So what happens is that on the one side, because V is positively transverse to X, the contraction of omega to the n, the contraction of the volume form with respect to V, is a volume form on X. But if I contract, well, this behaves like a derivative, so I've got n times the contraction of omega wedged omega to the n minus 1 restricted to X. And this is just n lambda, which d lambda to the n minus 1, because well, omega is d lambda, and definition of V. Well, and this is restricted to X, and this is just n alpha, d alpha to the n minus 1. So here alpha is just by definition lambda restricted to X. So this proves that if you have a submanifold in such a way that your Liouville vector field is transverse to it, then the restriction of the primitive of the symplectic form to the codimension 1 submanifold is a contact form. So in other words, X alpha, or alpha is lambda restricted to X, is a strict because it comes with a contact form, strict contact manifold. And in this situation, one usually says that X is a contact type. So what you really think is X should be the level set of a Hamiltonian. So, and let me just finish the first part of the talk by sort of stating that. The proposition, if X is a level set of a Hamiltonian inside symplectic manifolds, i.e., if X alpha is contact type, then if alpha is lambda restricted to X, then the ray vector field is a reparametration of the Hamiltonian vector field. So the Hamiltonian vector field of H restricted to X is some positive function times the ray vector field of alpha. This is strictly positive. In other words, Hamiltonian dynamics on contact type level sets is the same thing as ray dynamics. Okay, so if you're studying a mechanical system and you're lucky enough to have contact type level sets for some Hamiltonian, then studying the Hamiltonian flow of the problem is the same thing as studying the ray flow of the problem. So I'm gonna take a 5-minute break and then we'll continue.
Is it still recording?
So what?
Is that something, or is it?
Oh, sure. I mean, it's still on, whatever.
I wasn't here for this, so maybe I always get confused when people say maximally non-integrable.
Right.
Because doesn't it have to be integrable? Maybe some like half-dimensional space, or maybe.
Well, yeah, I mean, integrability should mean that there's a submanifold whose tangent space is precisely your
Right,
distribution.
when you say the contact form, or maybe its vector field, is maximally non-integrable,
I mean,
as much as is possible.
yeah, as much as
as
possible,
possible,
non-integral.
okay,
As
okay.
much as possible means
Yeah,
the
away from
dimension of the submanifolds is bounded by half
minus
dimension.
1, 2,
Yeah.
something like that.
If you are to n minus 1 dimensional, it's n minus 1. So in a 3 manifold, the Lagrangians are 1 dimensional. So they're just,
Okay, so that's what you mean. when you say
yeah,
maximum.
that's what you mean when you say maximum.
I'm too cold to focus.
Midi, j'ai discuté avec Georges. Et après, je fais de. Je mets du fromage sous huile avec des épices. Ça fait. Alors, ça t'a l'air bien. C'est très beau. Après, il faudra prendre une semaine pour.
Okay, I will press on then. So this whole discussion basically is tying up contact and geometric rules instead of trying to interpret them from a geometric perspective. So let me give you some further examples. So the fundamental examples are the following. So star-shaped domains. So X inside R2N is said to be star-shaped if it bounds a compact domain containing the origin, containing 0, and the standard Liouville vector field, which is V Q partial Q plus P partial P, is transfers to X. So here's X. It's the boundary of some domain, and the radial vector field is transverse to the boundary of the domain. Which is, imagine like a ball, or just the form ball, but still transverse to the radial direction. So if you have a star-shaped domain, then because V is precisely the Liouville vector field of the standard symplectic form associated to the standard primitive, the standard Liouville form, then X, lambda standard restricted to X, is contact type. In a particular case, well, S3 is the level set of a Hamiltonian, just the kinetic Hamiltonian. This is star-shaped. This is star-shaped in R4. And alpha, which is just the restriction of of lambda standard to S3, you can write it down and look something like this. So it's x1 dy1 minus y1 dx1 plus x2 dy2 minus y2 dx2. Well, here I'm using coordinates z1, z is z1, z2, x1 plus I, y1, x2 plus I, y2. And the ray vector field of this contact form is actually, you can write it down as follows. And the rate flow in complex coordinates is precisely parametrizing the Hopf fiber. So this is the Hopf flow. Okay, so in S3, the ray flow of the standard contact form is the fibers of the Hopf fibration, which is everything is periodic. And you should think Kepler problem. And another fundamental example is the unicotangent bundle. So here you put Q with a metric, so some Riemannian manifolds. And the unicotangent bundle of Q is just, well, those QPs with the norm of P equals 1. And this is just the level set of, again, the kinetic Hamiltonian. So H of QP is the norm of P squared divided by 2. So, I mean, you should think geodesic flow, right? I mean, we have a Hamiltonian problem here, precisely the kinetic energy. So if you look at the radial direction of the fibers, so P partial P, this is a radial vector field, is precisely the Liouville vector field of a standard Liouville form. And it's clearly transverse to the unicotangent bundle. Right? So here we have Q, and we've got the unicotangent bundle. And, you know, the radial direction is obviously transverse, so V is transverse to unicotangent bundle, and so, well, this guy is a contact manifold. Here, alpha standard is just lambda standard restricted to the unicotangent bundle of Q. This is a contact manifold. And the rate dynamics, as you can check, is the Hamiltonian dynamics of the kinetic Hamiltonian. This is just a geodesic flow. So in other words, you know, we achieved two dynamics which are sort of very well studied as a geodesic flow in terms of contact topology. So the class of ray flows is very large, so it contains in particular the geodesic flows and all of the dynamics on convex sort of star-shaped domains in R2N as well. Okay, so this was the sort of crash course in sort of contact and symplectic geometry. So now I will want to move on from the geometry and do some topology, and now sort of tie up the discussion on geometry with the previous discussion on topology on open books. This is open books in contact topology. And the key definition in this whole story is due to Emmanuel Giroux. And it's the following. So you start with some contact manifold at C. And you start with an open book by B on X. Then we say that the contact structure is supported by the open book if the following conditions hold. Then C is supported by the open book if there exists a contact form alpha which is called the Giroux form, satisfying the following conditions. Such that the first condition is that if I restrict alpha to the binding of the open book, this is called alpha B, then this is a positive contact form for B. And the second condition is if I restrict the derivative of alpha to a page, this is a positive symplectic form on the interior of B. For every page P. And here the words positive, I mean, they're important. So everything has to be oriented. So M, X, sort of, you should think that it comes oriented. The circle is naturally oriented. So if I have those two orientations that induce an orientation on the page, and once I have an orientation on the page, I have an orientation on the binding. So all the orientations need to be compatible. So, okay, what does this mean in terms of wave dynamics is the following. So you can check that this definition, this is equivalent to first condition is that the rate vector field of alpha restricted to the binding is tangent to the binding. And the second condition is that the rate vector field is positively transverse to the interior of each page. In other words, I mean, the rate dynamics of alpha is adapted to the open book. let me point out the following. So this definition is that there exists some alpha for the contact structure. So the contact structure is the one that's fixed here. Alpha is completely auxiliary. So the dynamical system is completely auxiliary. The geometry is fixed, though. So I will state a theorem now. And you should think of that in those terms. So the theorem due to Giroux in the 2000s maybe, I don't know. So if
It was announced at least in 2000. I mean, I heard it in 2000.
okay, so 2000.
And then, well, when he proved it, I don't know. When he wrote it, well, we all know.
I'm not gonna make any bold claims. I'm gonna say Giroux 2000. Then every open book. Yeah. Every open book supports a unique isotopic class of contact structures.
No, I wonder if in 2000 it was not only for dimension 3.
It was in any dimension, right?
In 2000, I'm not sure, actually.
Well,
When I heard about it in 2000, he was talking about dimension 3.
okay. So I don't know. Maybe 2000 is dimension 3. This one is the high dimensions. Who knows? Okay. Anyway, so every open book supports a unique isotopic class of contact structures, and any contact structure admits a supporting open book. So this is a very, very fundamental theorem and very hard theorem as well. As Paolo was pointing out, in dimension 3, it's also even stronger. So this is, I stated in any dimension, but in dimension 3, there's also even a uniqueness for the open books up to a suitable notion of positive stabilization. So what Giroux did in dimension 3 can be interpreted that you reduce the study of contact geometry to the topological study of open books. So this is why one calls the field of contact topology when the object of study is the contact manifold itself, because you can do it topologically in dimension 3, say. And this should be interpreted as a geometric theorem or topological theorem rather than a dynamical theorem, because as I said, the Giroux form is never fixed. It's completely auxiliary. You give me my contact structure and I adapt some dynamics for the contact structure. It's not that you give me a dynamics and I adapt the open book to it. So this is a different direction. It depends on whether you're trying to study the manifold itself and you're doing contact topology, or whether you're studying the wave dynamical system as opposed to the previous direction. Okay, so this is sort of the game. So in some sense, Giroux wasn't really doing dynamical systems. And here by isotopy, an isotopy is just a smooth path of contact structures, which by theorem called gray stability, if you have two isotopic contact structures, then they're actually isomorphic. Anyway, so yeah, let me state the Giroux correspondence in dimension 3. I mean, I will not explain everything, but just trying to explain Giroux correspondence will take me just a whole semester. But the manifold is 3. then sort of a class of contact structures up to isotopy with an 1-1 correspondence with open hooks up to positive stabilization. Okay, so as I said, roughly speaking, it reduces the study of contact manifolds to the study of open books. So, yeah. So basically what I'm headed to is, trying to use the insights from Giroux correspondence in the three-body problem. Roughly speaking, one can say that that's what we did in our work with Otto. I mean, the insight came from here. So this is all that I want to cover from sort of contact symplectic geometry / topology. So maybe let me go back to the circuit three-body problem, state a theorem. So this is contact geometry and the restricted three-body problem. So let me recall that we have Moser regularized level sets, which are denoted by sigma CE, which is the component near the Earth, and regularized level set near the Moon. And then we also have the connected sum component. So these two are copies of the unit cotangent bundle of S3, and this is a copy of the unit cotangent bundle of S3 connected sum, the unit cotangent bundle of S3 again. These were the level sets after Moser regularization of the Hamiltonian in the restricted three-body problem. The components of the level sets near the Earth, near the Moon, and sort of the connected sum once we cross the first critical value. And the theorem, due to a bunch of people. So first of all, it's due to Peter Albers, Urs, Frauenfelder, Otto, David Paternine. This is in 2012. So they did the planar problem. And then some students of Otto did the spatial problem. So Jung and Kin. This is more recent. This is 2018. So what they say, so this is the spatial problem, is that, well, all of these regularized level sets are contact type. So are all, these are, just put it like this, they're contact type. So remember that here, C is subcritical, so it's below the first critical energy value. And then sigma, the connected sum components, is also contact type. If the energy is slightly above the first critical value of C. plus epsilon, which epsilon here is sufficiently small. And sufficiently small, well, it's not clear how small it needs to be in principle. But so as contact manifolds, they're not, geometrically, they're not very interesting, but dynamically they are. That's the whole point. So here, as contact manifolds, they're both isomorphic to the standard contact structure. So the standard contact structure on the Unicode tension bundle of S3. And the connected sum is the connected sum, but in the contact category. So there's a notion of taking the connected sum of two contact manifolds, and I still get a contact manifold, and this is what I'm using here. Formally, you need to think, well, there's some Weinstein one-handle attachment. You know what that is, and if not, just believe me. Okay, so in other words, for low energies, we can do contact geometry in the restricted three-body problem. So low energies means I stay near the Earth, near the Moon, or I have sufficiently enough energy, but very small still, to do the transfer from one to the other. And let me mention that sort of it's not really known whether the contact condition fails for sufficiently high C, for sufficiently high Jacobi constant. I mean, there are some people looking at this in Augsburg. I think there was a student of yours, was it like Robert Nichols, I think, who was like looking at whether you can actually prove that the contact condition actually fails. So they actually have strong evidence to suggest that the contact condition actually fails if you go up sufficiently in energy, because you could find some orbits with negative Rabe action or negative action, which so it cannot be a Rabe orbit because Rabe orbits have positive action. So something like this. So, but I mean, you can say it's not known, and maybe yours can sort of tell me otherwise. But in principle, we don't know whether we can sort of go up up to, I don't know, H of L2, say.
Yeah. No, Robert is writing down this.
He's writing it down? Okay. But so you actually prove that that it fails?
Yeah, he has examples.
Okay, cool. Okay, so do you know how much it fails? Like how high up with C you're?
No, it's for higher energy. It's around zero, a bit below zero.
A bit below zero. Okay.
Yeah.
What is below zero? The energy.
Yes. The energy is below zero. Is kind of the Magne critical value. Above.
Okay. Okay. Fine. Okay. Thanks. Anyway. Okay. So let me do a very short digression before I'm not going to have too much time today to talk about Hofer-Wysocki-Sender. So let me just talk about open books and Lefschetz variations. So before I do this, I mean, it follows as a corollary from this that in order to understand the dynamical system in this energies, we just need to study the Rabe dynamics for the contact form that we obtain. Contact form is just a restriction of the ambient, the standard contact form in the picture after regularization. Anyways, so open books and Lefschetz variations. So again, I'm going to do some topology. Let me do a smooth version first. Before, so I talked about open books and the smooth category, and then sort of upgraded to the contact category via Giroux correspondence. So let me just define what a Lefschetz fibration is. And the definition comes from algebraic geometry. So, I'm going to define in dimension 4. So assume that M is a compact four manifold with boundary. So a Lefschetz fibration on M is a map phi from M to a surface S. So here where S is an oriented surface with boundary. Satisfying the following conditions. Such that each critical point of pi lies in the interior of the manifold and has a complex chart Z1, Z2, and C2, such that, well, pi looks like a Morse, well, the critical point looks like a Morse critical point in the complex sense. So pi of Z1, Z2 is the sum of the squares of Z1 plus Z2. So the point P corresponds to 0 in this local chart, and this is a critical point of this function, and well, it looks like a node. So let me draw a picture. So the picture is, well, here's, imagine like the case of a two-disk. So S is a two-disk, and well, we have a fiber. Well, the fibers of this map are two-dimensional. So you could think you'd have like a point, like the fiber or a point looks like this, but at some point, you could develop singular fibers. And you should have like a nodal singularity. So here's a critical point. This is a critical value, right? But here I've got like a local chart on which this whole picture looks like the standard model for Lefschetz fibration. I just zoom in on this little box here. What I see is this. So here I've got a two-disk, and here this is a P star is 1, so an annulus, and this is a singular node, which is obtained by sort of pinching down the pseudo-section of T star is 1 to a point. So this is called the vanishing cycle. So in other words, a Lefschetz fibration is a vibration away from a finite number of nodal type singularities. This is a spider. Anyway, so the regular fiber is just a surface. Well, it's a surface with boundary. And sort of the critical points are nodal. And so we have vanishing cycles. Let me call the regular fiber F. So this is a vanishing cycle V inside F. So V is a copy of S1. It's a circle in the fiber, and this has to shrink down to a point where you see the nodes. And so Lefschetz rotation, as I said, that comes from algebraic geometry, where people were looking at sort of pencils of conics and B2 or stuff like that. What I'm interested in this notion is that when I look at the boundary, what I see is precisely an open book decomposition. Right? So what happens if I look at the boundary of this? You can think of like, I have two lids. I have like the horizontal boundary, the horizontal boundary, which looks like this, and then I have the vertical boundary, which projects down to a circle. Let me just. The boundary of M is a copy of the vertical boundary of M, union the horizontal boundary of M. So here, the vertical boundary is the image of the boundary of the surface. And the boundary, the horizontal boundary of M, is just a union over points. Let's say, let's focus on the case S equals D2. Say. So it's a union of points on D2 of the boundary of the fibers. So this is the horizontal boundary, and then everything that fibers over the circle is the vertical boundary. So because I'm looking at the case of D2, well, necessarily, the fibration on the boundary, because I assume that there are no critical points on the boundary, on the boundary I have a fibration over S1. So fibrations over S1 is just mapping tori. So necessarily, the vertical boundary is the mapping torus of some monodromy, which is precisely the monodromy what I get if I go once around the circle. So this is P phi. So this is the mapping torus of some monodromy. This is the mapping torus. And here the monodromy, phi is the monodromy of the fibration of phi restricted to the boundary of the disk. And well, as it turns out, because you have a local model and everything is sort of complex, the monodromy cannot really be anything, but it has to be necessarily a product of positive dangerous around the vanishing cycles. So this has to be by looking at what happens at a local model. So on the local model, you can check that the monodromy is, the Dane twist around this guy. So if you go once around, so I look at this guy here, I go once around, and I come back with a Dane twist. If I go once around like this. So if this is the vanishing cycle V, which is the zero section, so the monodromy phi in this picture is just T V, which is the Dane twist along B. And sort of, this is all a local picture. So the global picture is for each critical point, you pick up a positive Dane twist. So positive means like right-handed, right? So according to the orientation. So this is the product of phi equals 1 up to n, where n is the number of critical points of Dane twist along the vanishing cycle Vi. So here, where V1 up to Vn is the vanishing cycles. Okay, and well, that's a vertical piece, and well, the horizontal piece is a fibration over the disk because there's no critical points again, but that has to be necessarily a trivial fibration. So in other words, it's just the boundary of the fiber times the two disk. So necessarily, horizontal boundary of n is B times D2, where B is the boundary of the fiber. So here, B in this picture, it says collection is this two circles. This is B. So what I just obtained is that the boundary of n is the open book whose page is the fiber, the regular fiber of the Lefschetz fibration, and the monodromy is a product of positive Dane twists along the vanishing cycles. So usually I will denote the data of, if you give me the fiber, the regular fiber, if you give me the monodromy, so I will denote M is the Lefschetz fibration with fiber F and monodromy phi. This is a bad notation because it doesn't really depend on phi. It depends on the decomposition of phi into a product of things, but I will just use it anyways. So the motto that, you know, what we just proved is that the boundary of the Lefschetz fibration associated to regular fiber phi and monodromy F and monodromy phi is the open book for the same data. Okay, so this is sort of the topological smooth statement that I wanted to make. Of course, so far this has been a smooth discussion, so this can also be upgraded to the symplectic category. So now I did the smooth version, let me do the symplectic version. Which you should think, you know, this is the Giroux notion in this setup. So a symplectic Lefschetz fibration, or let's say an exact symplectic Lefschetz fibration on a symplectic 4 manifold is the Lefschetz fibration phi, for which the horizontal and vertical boundaries are convex. This means that the Liouville vector field is outwards pointing along each of them. And moreover, the fibers are symplectic. which means that the restriction of omega to the fiber F is symplectic. And it also has convex boundary. So let me draw a picture. So the picture is something like this. So you've got the horizontal boundary, and you've got the vertical boundary. And sort of the Liouville vector field points out, also points out here. And you can sort of, you can smoothen the corner so that the boundary becomes a smooth manifold. And so the boundary is contact type. So in other words, the boundary of M is contact type. And well, so it inherits contact form just by restriction of lambda. And so here, psi, the kernel of alpha is by definition supported by the open book at the boundary. Okay, so in other words, I mean, I define a notion of what it means for an open book to support a contact structure. I define a notion what it means to have a symplectic Lefschetz fibration, and the two notions are compatible. Right? So when I look at the boundary of my symplectic sort of Lefschetz fibration, I obtain a contact structure supported by the natural open book that I see at the boundary. Okay? So this is sort of the geometric picture to have in mind. So there's some sort of algebraic geometric situation which I have nodes and sort of divisors and whatnot. And I have a geometric picture as well, but I also have some dynamical picture that you should sort of remember. Let me sort of write down an example and then sort of finish off for today. So the fundamental example that I want to look at is when I look at D star S2. So the unit disk cotangent bundle of S2, this is the Lefschetz fibration whose regular fiber is a D star S1, and its monodromy is a square root of the dense side of the dangerous. So here T rho is the dangerous. On D star S1. And so by taking boundary of on this Lefschetz fibration, which is RP3, we get the open book on RP3 that we already discussed. So and the picture to remember is, so this is what the Lefschetz fibration looks like. So here's the two disk. The regular fiber is the D star S1. Here's the zero section of D star S2. Here's the south and the north pole, X minus and X plus. And the zero section of the Lefschetz fibration sort of projects down to this interval, joining the two critical values. So there are precisely two singular fibers. And what you should think is when I take the boundary of this thing, I get the geodesic open. This is concretely is a geodesic open book. Okay, So yeah, I'm done for today. So thanks everyone for coming. And so next time I'm gonna try to do for real. So probably I won't have time to discuss all the work that we've done with Otto. So maybe I would like to add another session, on which I will. So we'll see what happens on next section. So any questions from guys in Zoom? So there was a lot of stuff happening today. So I guess you have to do some reading first. Anyways, I'm going to stop the recording.
What did you say, Agustin? Did you say you are planning to make a reading course?
I said that I might do another session to explain the results with Otto.